Gonna see if we can get our Elmo to go. We are into day 2, folks. Day 2, combinations. There are differences between a combination and permutation. It's still counting the number of arrangements, but with a combination now, the order does not matter. Okay, the order does not matter. I'm going to show you a couple of scenarios where that happens, where the order doesn't quite matter, and hopefully it makes sense to you guys. So let's take a look. It says 5 students are running for a student council cabinet. Now this is different than like a president, vice president. Cabinet members are just cabinet members. It doesn't matter if you get the most votes or the second most votes. As long as you're one of the 2 people who gets the most votes, you're going to be in the cabinet. So you'll notice here that the order in which they get picked doesn't matter if they get the most or not. So create a system of symbols to represent 5 students. Again, let's go ahead and let it be A, B, C, D, and E. And now it says, use those symbols to list every combination. Well, we could have AB, could have AC, could have AD, could have AE. With B now if you think about it, so BA is going to be the same as AB, so it's out. But we still have BC, BD, and BE. With C, we could have had CB, which is the same as BC. We could have had CA, which is the same as AC. We could have CD and CE. With D, we could have had DA, which is the same as AD. We could have had DB, which is the same as BD. We could have had DC, which is the same as CD. And we could have DE, which we don't have. So now with E, we could have had EA, which we already have. We could have had EB, which we already have. We could have had EC, which we already have. We could have had ED, which we already have. So in other words, how many different ways could that happen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 different ways, okay? We have 10 different combinations, if you will. We have 10 different combinations of those 2 students. Now, you might be saying, man, do I really have to do this out every time? But again, no, you don't have to. But sometimes it is very beneficial to do down C. The way we represent combination is with C. N is still the number of people we're choosing. R is how many we're going to choose or how many spots there are. You can denote it this way, or this way. So if you see any of these 3, you know it's a combination. Remember, permutation is just with the P. So let's go ahead and try and see how to do this with so if we're doing the same scenario up here, 5 students running for 2 positions, 5, choose 2, you would write it one of these 3 ways. You can actually now go to your calculator, and you could, so notice how we had NPR? We now want this to be an NCR, so we put 5, go to math, go back to PRB, and notice the third one now says NCR. We hit 2, and it comes up with 10. Well, yeah, we already knew that was 10 because we calculated it out, but your calculator can do it for you as well. There's 10, okay? I'm going to show you now how kind of these 2 things work together, if you will. Whew, sorry about that. Sorry about that. It was kind of crazy. If the original 5 students were running for a president and vice president race, where it matters who gets the most votes, how can the list above make a list of these presidencies? Well, so now up above, instead of crossing out any of them, we would need all of them. So in other words, none of these would cross out. So we would say that there's 1, 2, 3, 4 in each one, and there's 1, 2, 3, 4, 5 options for the first person. So that would be 5 times 4 or 20. Or in other words, we didn't take out any of them, so they're all there. So there's 20 different ways for that to happen. We would say this is a permutation, so we would have 5P2 giving us the 2 slots, 1, 2, 5 times 4, which of course is 20. Okay? Now if we look at it, it says, suppose Abe and Barb won the cabinet race. If they had been running for president, VP, there would have been 2 different ways to make the presidency, which means the list in number 4, which is here, is twice as many as the list in number 2, where there wasn't. So, and you can see that 20 is twice of 2. Thus, for the list above, we would say that 5p2, not 5c2, sorry, 5p2 is equal to 2 times 5c2. That tells us that our permutation will always be greater than or equal to our combination, okay? Permutations are always greater than or equal to your combinations, and that's just will always happen because sometimes they will be equal. Sometimes they will be equal. That is true. So let's go ahead and take a look. Okay. So as you're filling, and here's another option for us. You're filling a bowl with 3 scoops of ice cream using 4 different flavors of ice cream. You may not repeat the flavors. It says how many different 3-scoop bowls can be created using the 4 flavors. Well, again, so you have 4 flavors, and you're going to choose 3 of them. The question is does the order matter? Well, if it's in a bowl, like if they put in strawberry, chocolate, then vanilla, and you want to eat vanilla first, no problem. You just turn to vanilla, eat the vanilla first. So so it doesn't matter the order in which they come into the bowl. So therefore, this is a combination, which is kind of different than like an ice cream cone. Because if an ice cream cone, if they put strawberry, chocolate, vanilla, and you want to eat vanilla first, your ice cream cone is going to fall over because, I mean, you can lick the vanilla first, but you can't eat the vanilla. Because if you ate the whole vanilla, the chocolate and strawberry would just fall off. So that's not going to work for you. So how many different ice cream bowls are there? 4 combination 3, which, okay, so how can we do that? We could make a list. We can make a list out again. We have our chocolate, vanilla, strawberry, chocolate, or it could have been chocolate, vanilla. Doesn't say what the others. Let's say it's pecan, or it could have been chocolate, strawberry, pecan. Or let's see, so chocolate, vanilla, strawberry, chocolate, vanilla, pecan, chocolate, strawberry, pecan. I don't think there's any other options there are. Because if we try to move pecan in, it just makes it the same thing, right? Like chocolate, pecan, vanilla is the same as this one. Chocolate, pecan, strawberry would be the same as that one. Chocolate, vanilla, pecan, or pecan, vanilla. Yeah, no, it's all the same. So, get those 3. Now, if we go from here, we could do vanilla, strawberry, pecan. We don't have that option yet. If we tried vanilla, strawberry, chocolate, we already have that option right here. If we try vanilla, chocolate, pecan, we have that option right here. If we tried vanilla, pecan, strawberry, we already have that option up there. And okay, so there's really only 4 ways for this. There's only 4 ways to make those bowls happen. Let's see on our calculator if that's true. If we type in 4 math, go over to PRB down to NCR, hit in 3, comes out with, it does come out with 4. Okay, so now we're going to try to see if we can see the connection between the permutation combinations. You're making 3 scoops of ice cream cones, so now they're ice cream cones, using 4 different flavors of ice cream. Since you're particular about the order you eat the flavors, the order matters. So therefore, this is a permutation because the order matters. So how many different 3-scoop ice cream cones can be used using 4 different flavors? So it'd be 4 P3, so in other words, 1, 2, 3, 4, 3, 2. 4 times 3 is 12, times 2 is 24. So we just got 24 different ways. How are the permutations and combinations in 3 factorial related? Well, we know 3 factorial happens to be 3 times 2 times 1, which is 6. And if you look at it, what is 24 divided by 6? Well, that's 4, which is how many combinations there were. Oh, So in other words, 4C3 is the same thing as 4P3 divided by out our 3 factorial. So you can see that's where we end up right here. This gives you NPR, but if you look at NCR for the factorial, which is kind of what we did right here, it's equal to the permutation divided by that R factorial. You're dividing out those ones that represent the exact same poles or same things for your combination. All right? So, here we go. Let's say that you have 7 students running for a 4-person presidency. So that'd be 7P4, which would be 7 times 6 times 5 times 4. Permutations of possible 4-person presidencies. Now, if you each cabinet can be arranged. So now it says each cabinet or bowl can be arranged into 4 factorial ways. So that's going to be 4 times 3 times 2 times 1, right? Therefore, if the 7 students are running for a cabinet, there are our permutations, 7 times 6 times 5 times 4 over the 4 factorial, 4 times 3 times 2 times 1, which the 4 simplify, 3 times 2 is 6, you just get 35. 7 times 5 is 35 again. Right here we wrote it up for you. Sorry, I wrote it up for you right here. 4, 3 times 2 is 6, 7 times 5 is 35, or 1 is 35. That's how you do combinations, folks. It's that simple. Let's look at some, let's try some. Assume there are 9 students running for the cabinet. How many different 4-person cabinets could be created? Okay, so it'd be 9C4, since it's a cabinet, order doesn't matter. So I'm going to first take 9P4, and I'm going to divide it by 4 factorial. So 9P4 means I have 4 slots. Start with 9, 8, 7, and 6. Divided by 4 factorial, 4 times 3 times 2 times 1. 4 times 2 is 8. So I'm going to take out that 8. 3 goes into 6 twice. 9 times 7 is 63 times 2 be 126. 126 different ways. Assuming that Walter, Xander, Yvette, and Zeke made the cabinet, the new principal decides he would turn the 4-person cabinet into a 4-person presidency, how many different ways could she arrange the 4 students in the new presidency? So we have 4 people. We're going to take 4 people, and we're going to arrange them into a 4-person presidency. So that's going to be 4 slots, 4, then 3, then 2, then 1. This is just a 4 factorial. So 4 factorial, 4 times 3 is 12, times 2 is 24, times 1 is 24. And assume instead of that 9 students running for presidency, assume instead that 9 students running for the presidency. How many different 4-person presidencies could be formed? Well, we just this would be working it kind of backwards. We found the combinations. This is the factorial. You could just multiply those 2 together. You could take 126 times 4 times 4 factorial, which would be 126 times 24, which, using a calculator, we get 3,024. We could look at it as 9. We have a 4-person presidency. 1, 2, 3, 4. 9 times 8 times 7 times 6. Go ahead and check it out. 9 times 8 times 7 times 6. See what you get. The same number, 3,024. Okay, find the following combinations by hand. 3C2. So I would tell you to do a 3P2 over a 2 factorial. So that means I have 2 slots. 3 times 2 over 2 factorial, 2 times 1. That's just 3. 5, choose 1. That's going to be a 5P1 over a 1 factorial. So 1 slot, which is a 5, and then over 1, which is 5. Okay, 2, choose 0. Means I have 0 slots. I'm going to choose 2 of them. There's only one way to do that. That's not to choose any of them. So there's that 0 arrangement type idea again. 7, choose 4. So that's going to be a 7P1 P4 over 4 factorial. That's 1, 2, 3, 4, 7, 6, 5, 4 over 4, 3, 2, 1. 4's go, 3 times 2 goes, 7 times 5 is 35. 10C3, that's going to be a 10P3 over a 3 factorial. So that's going to be a 10, so there's 3 slots, 1, 2, 3, 10, 9, 8, that's the permutation part, divided by 3 factorial. 3 goes into 9, 3 times, 2 goes into 8, 4 times 3 is 12, times 10 is 120. Okay? Again, you could do it on your calculator. Let's just check this last one out here. So we go to math. Oh, before we go to math, we got to type in the 10, 10. Now to math, over to PRB, down to NCR, type in 3, and I get 120. It checks. All right, folks, there you go. You are now ready to do the homework. Good luck. Combinations, order matters. Permutations, order does not matter. Have a good one. Bye. Oh, baby, I can't spell. Combinations.